Here, and this is the 2020 AMC 12B problem 23. Here's a view of this problem. For how many integers n greater than or equal to 2 are there such that whenever, actually a keyword here being whenever, z1, z2 all the way to zn are complex numbers such that the modulus of everything is 1 and the sum of everything is 0, then the numbers are equally spaced on the unit circle in the complex plane. Now the reason I underlined whenever is because we can always choose our z sub i's to satisfy this condition by simply letting the z sub i's be the nth roots of unity. If we do that, then we indeed have that their modulus is 1, the sum of the nth roots is 0, and they are equally spaced out. So this whenever is actually very important in this problem. So let's start experimenting. How many integers n greater than or equal to 2? Well, what happens when n is equal to 2? When n is equal to 2, let's just draw a little circle. The circle has a radius of 1. What happens is, no matter what z1 we choose, suppose we arbitrarily choose it over here, we can always choose a z2 such that the sum negates to 0 by simply choosing it to be diametrically opposite. Therefore, we can always choose z2 to be negative z sub 1, and hence we always have them spaced out if n is equal to 2. However, when n is equal to 3, now when n is equal to 3, it gets a little bit more complicated. Specifically, when we have a circle with radius 1, we need to show that if the roots are of modulus 1 and they sum to 0, then they must be equally spaced around the circle. Or in other words, that they have a 2 pi over 3 radian distance away from them, right? So how can we show this? So we want to say if z1 is equal to re to the I theta, z2 is equal to re to the I times theta plus 2 pi over 3. Again, just an angular counterclockwise rotation by 2 pi over 3 radians. And then z3 is just this plus 2 pi I over 3, which is 4 pi I over 3. We want to show that only if it's in this format will the sum be 0, because it's pretty clear that the modulus is already 1. So, well, there's really nothing better to do other than expand this. We get r cosine theta plus ri sine theta plus r cosine theta plus pi over 3, theta plus 2 pi I over 3 plus ri sine theta plus 2 pi over 3. And then finally we have r times cosine theta plus 4 pi I over 3. And then plus I sine, ri sine theta plus 4 pi over 3. Now perhaps we can evaluate everything with sum to product, but I'm actually just going to group it to become a little bit neater. Factoring in r for all the cosine terms, we get this. Cosine theta plus 4 pi over 3. And then plus ri sine theta. Again, if this was on paper, it'd be much faster, but you're going to have to deal with this from now on. 2 pi over 3 plus sine 4 pi over 3. Okay, so let's see what this evaluates to. Cosine theta, we can split this using sum to product. Sum and differences. Cosine theta, cosine 2 pi over 3, that'd be negative 1/2 cosine theta. And then minus sine theta, sine 2 pi over 3, that becomes negative root 3 over 2 sine theta. And then this becomes cosine theta, cosine 4 pi over 3, which is just negative 1/2 cosine theta. And then minus sine theta, sine 4 pi over 3, that becomes negative sine theta times negative root 3 over 2, or plus root 3 over 2 sine theta. And we see that this cancels, this becomes negative 1, which cancels with this goes to 0. Okay, what about this? Sine theta, and then using sum to difference identity, sine theta cosine 2 pi over 3, that becomes negative 1/2 sine theta. And then minus cosine theta sine 2 pi over 3, that becomes negative root 3 over 2 cosine theta. and it becomes sine theta cosine 2 pi over 3. That becomes negative 1/2 sine theta again, and then negative cosine theta sine 4 pi over 3. So that becomes double negative positive root 3 over 2 cosine theta. Cancel, 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 cancel. So we see that if they're spaced to like 120 degrees, we see that the sum is 0, therefore n equals 3 works. But now we can actually make a construction for n equals 4 such that this doesn't satisfy. Suppose we have roots. We just saw that two roots must be diametrically opposite in order for their sum to negate to 0. But now we can actually construct some other roots, say these two things, such that when these roots are sufficiently close together, the sum still negates to 0. But look what happens over here. We can always make this angle greater than the other angle such that they are not equally separated. So we can see this, and by similar construction, we can cancel out every other n. So by this construction, we see this can't work. Therefore, n equals 2, n equals 3 are the only values that work. Those are b values, and we are done.